Alright, moving right along, we've got more related rates questions. Goodness. A water tank is drained. The following function gives the volume remaining after t minutes from when the drain is opened. What is the instantaneous rate of change in the volume after 10 minutes? This one's actually kind of nice. We just need to know the change in volume at a certain time, and we know the original volume function. So all we have to do is derive that volume function, so v prime of t. That 3000 is just a constant out front, so it's going to remain out front. Up next, we have a chain rule going on here. We derive all of the inside. The 1 derives to 0, and the t derives to 1, so we just have that constant negative 0.05 tagging along. Then we have a power rule going on the outside, so we drop the power of 2, keep the inner contents, and now it's to the first power, or in other words, it's just a set of parentheses. And the question is, what is this whole thing at 10? So I'm going to plug in 10 and I'm going to start simplifying things simultaneously. So let's see here, 3000 times negative 0.05 times 2, that's just negative 300. All of this on the outside. On the inside, 1 minus 0.05 times 10 is just 0.5. And so it looks like the answer is negative 150. And now we need to know what units we're going in. And again, it's always like length or amount divided by time. That's how we describe derivatives. All right. Once again, volume questions. The side of a cube is increasing at a rate, so that usually we'll call side like S. And so that's the rate of change, so ds dt, it's increasing at 2. And at a certain instance, s is 1.5, and the trick to this problem is probably writing that as 3 over 2 to make it easier for yourself if you don't have a calculator. And the question is, what is the rate of change of the volume? Well, just remember that volume of a cube is just s cubed. And so if I want dv dt, I'll derive the other side and I'll get 3s squared ds dt, and now I just have to plug in s and I have to plug in ds dt. So I have 3 times 3 over 2 squared times 2, and this is why I chose to write this as a fraction, because I knew I was going to be squaring this in a second. So that's 3 times 9 over 4 times 2, and that all ends up being 27 over 2. And its volume, so yeah, cubic kilometers per hour. If this were the AP exam or free response question, just make sure that you put the units in there. That's always, always, always going to be a big point on the exam. All right, up next. Linear approximation. Speaking of things that would probably end up on the AP exam, linear approximation is definitely a good one, because linear approximation also is really tied to the equation of the tangent line. So first thing, like I was saying, it is related to the equation of the tangent line. So let's write the equation of the tangent line, which would be y minus y1, or the y value of your function. We set that equal to the slope at the value of interest, x minus the x value of interest. So we have x1, we have y1, and that's coming from this first block, x1, y1. And then we have the slope at x1, and that's how you start your problem off. And now we're trying to approximate what the value of 6.9 is. So what we do is we plug in 6.9 here. Some things to realize is that this is really plus 2 when you simplify it. Our goal is to find y, so what I'm going to do is I'm going to write it like this. If I had plus 2 over here, then now I have negative 2 over here. If I plug in 6.9, you just get negative 0.1. Oops, sorry, negative 0.1. I'm jumping ahead. Now, when you have 5 times negative 0.1, well, that's just negative 0.5 minus 2. And so that means our answer is just going to be negative 2.5. And there we go, linear approximation. The, I guess, general form of linear approximation, because sometimes they'll say they won't give you all this information. They'll actually give you a function itself, And then what you have to do is you need to plug in the value of x to know the y value. Then you need to derive the function and plug in the value of x to know the slope. Then after you find all that information, now you plug in the value you want to approximate. The big key there is to make sure that you only use the ugly one, the decimal, at the very end. Or in other words, only plug in the thing you want to approximate at the very end after you've already formed the equation of the tangent line. The equation of the tangent line should always use stuff that you can, I guess, plug in easily. That's the whole point of approximation. Using easy points to plug in to just use one difficult thing at the end. All right, up next we have a particle moving along the x-axis, and we have its position given by this function, and they want to know the velocity at 4. All you have to do is derive this and plug in 4. When you do that, that'll be 2 times 4 minus 10, so that's negative 2. And so that must mean it's moving to the left. In other words, it's moving in a way that is negative, and negative is left in this case. All right, up next, find the limit as we approach 0. This is a really special looking question, and it looks like this is our first instance of really diving into L'Hopital's rule for real. So I don't know about you, I don't feel like doing trig identities, but hopefully if we plug in 0 initially, 0 times 1 is 0 in the numerator, and then 0 plus 0 is 0 in the denominator. So following AP steps, first thing we want to do is say that the limit of that whole function, write it all down, equals 0 over 0, and we call that indeterminate form. And now we can apply L'Hopital's rule. And that means we can now take the limit as x approaches 0 of the numerator derived, which is a product rule, so give me a second. When you work out the whole product rule, I'm skipping ahead here, you're going to end up with cosine squared minus sine squared. Just trust me on that. It should have a plus sign in between, but when you derive cosine, you'll get negative sign. And again, your order can be a little bit different than mine, but essentially when you derive the numerator, you should end up with a positive cosine squared and a negative sine squared in some order. From there, when you derive the denominator, you get a 1, and then you get a 2 from the chain rule, and then a cosine when you derive the sine and put back the original contents. So now when we take the limit as we approach 0, let's see what happens here. Cosine of 0 is 1, so now we have 1 squared minus sine of 0 is 0 squared, all over 1 plus 2 times cosine of 0, which is 1. So now I end up getting 1/3. And there we go. All right, up next we have a differentiable function. This is just kind of the intro to related rates. So they also give me dy dt and dx dt. Or they give me dy dt and they want dx dt when y is 2. So in other words, what this function or this question is saying is derive this implicitly. In other words, follow this as if it was related rates in respect to time. Just recall that 1 over y is really y to the negative first. So when I derive that, I'm going to get negative 1 y to the negative 2, or in other words, negative 1 over y squared, and then also a dy dt, because we're deriving with respect to time now. That's equal to, careful, 8 derives to 0, and negative x just derives to negative 1, and then dx dt. dx dt. All right. So again, the question is find dx dt. Well, technically, I just need to multiply everything by a negative, or really, I'll get dx dt by itself once I solve for positive 1 over y squared dy dt. And we just have to plug in y as 0.2. So 1 over 0.2 squared. 0.2 squared is actually 0.04. And then dy dt is negative 0.5. Why would they do this to me? I can do this. Well, here's a fun thing to do for the sake of it. 0.04, notice this is in the hundredths place, so this is really 4 over 100, And since it's over 1, it's actually going to be flipped. It's going to be 100 over 4. And then negative 0.5, just remember, is negative 1/2. So it looks like this is going to be equal to negative 50 over 4, which is really negative 25 over 2. Gosh, I hope I'm right. Yay. All right, last but not least, we have a limit to infinity question. Now this, again, is a L'Hopital's rule question. If your goal is to take Cal 2, the other way to think about this is a growth rate question. Which function grows faster? The function in the numerator, which is really just a polynomial, or the exponential function? And hopefully you know by the name, exponential will grow faster. So essentially, you have something that's not growing as fast over something growing very fast. In other words, you have something that's going to end up being, in the long term, small over very large. And that approaches 0. But let's do this by L'Hopital's rule. If you plug in infinity, your indeterminate form this time will be infinity over infinity. So you say indeterminate form, you write apply L'Hopital's rule. Now you derive the numerator, which is going to be 5 minus 4x. Now you derive the denominator, which has a chain rule going on, but the chain rule for that little exponent is actually just a 1, and then an exponential derives to its original self. So now again, we're going to try to take the limit to infinity. Now this time technically we get negative infinity over infinity still, so we would write that, negative infinity over infinity, indeterminate form, apply L'Hopital's rule. Let's derive this one more time. This time we get negative 4 over, we get the same thing this time. Now when you plug infinity, you get negative 4 over infinity, which was what I was saying before, something small, relatively, over something very big. But what I missed is, oh, never mind, small over very big is actually approaching 0. I was about to say negative 0, but that doesn't matter. And so we're done.